want to prove both parts of the fundamental theorem of calculus. But before we do that, we need to think about the mean value theorem for integrals. So here we have the graph of a function that's continuous on this closed interval AB. And let's consider the integral on that interval. This integral, the integral from a to b of f of x, has an interpretation. We know that its value can be represented by the area below the curve and above the horizontal axis from a to b. So it's this area in here. Okay, with that in mind, let's think about the area of this rectangle. Now this rectangle is found by using f of a as the width and delta x as the length. In other words, b minus a is delta x. Obviously, that area is less than the total area under the curve. So we would say that the area of that rectangle is less than the integral. Now we could go the other way. We can say, well, let's consider this rectangle. Now we have a rectangle has a length here of f of b and a width of delta x, and its area is bigger. It's greater than the value of the integral. So we know the value of the integral is actually less than the area of that rectangle. And if you think about it in the light of the intermediate value theorem, if this integral is greater than, if the value of this integral is greater than the area of the small rectangle and less than the area of the large rectangle, you realize that actually I could draw lots of rectangles, and each time I could let the width be delta x and the length be f of some value of x in between a and b, and I would get rectangles of all areas between the area of the smaller rectangle and the area of the larger rectangle. Now, at some point then, I would have to have a rectangle with the area that's exactly the value of the integral, because we're going to take on all values between the smaller rectangle, f of a delta x, and the larger rectangle, f of b delta x. So somewhere in there, I have to have a rectangle with exactly the area of that integral. So in other words, what I'm saying is there exists a z in between here where I can say, okay, I'm going to make a rectangle that has the f of z times delta x. That area right there is going to be exactly the same as that integral. So we would say this is a true statement for some z between a and b. Now, this is what we're going to use in doing the first part of our proof for the fundamental theorem. So here we go. We've got the fundamental theorem of calculus part 1. Now, let's consider an integral here. Or let's consider a function, f of t, and let's suppose it's continuous on this closed interval AB. Now, what I want to do, and I'm saying this curve is the graph of f of t. What I want to do is just define a function. Big F of x is equal to this integral right here. And what I want to prove is that big F of x is actually an antiderivative of little f of t here. I want to prove, in other words, I want to prove this. F prime of x is equal to f of x. So that f of x is an antiderivative of f. Big F is an antiderivative of little f. Okay, so I want to start off by just finding the derivative of big F of x. So I do that just using the difference quotient. I go back to the definition of a derivative, and here it is. And then I come over here and say, well, instead of writing big F of x plus delta x, let me just write what it is, the integral. So here it is. Now, let's see if we can simplify this a little bit. If you think about it, this part right here that I've put a box around, that represents the area from a all the way over to x plus delta x. That's what that is. Now, if you look at the next part, what we've done is we've actually subtracted off this part. See? Because we're subtracting off the integral from a to x. And what we're left with is this, the integral from a to x plus delta x. So this right here can be rewritten this way. Now I go back and recall the intermediate value theorem for integrals. And I know that inside, between x and x plus delta x, there's a z, so that I can rewrite this integral as f of z delta x. So I'll do that. I'll just replace the integral with f of z delta x, and notice the delta x's cancel, and I just am left with this thing. Now think about it. This limit. If delta x is going to 0, that means this point right here is moving in this direction. That means z is moving toward x. So we could write this limit as the limit as z goes to x of f of z, and of course that equals f of x. And that is precisely our proof. So what we found is that f prime of x is big F prime of x is equal to little f of x. Now let's look at the second part. The second part says that if you have an integral like this, so and we're saying that f of x is continuous on a closed interval ab, we're saying that that integral can be evaluated this way, where big F is an antiderivative of little f. So in other words, you can just plug in the top bound and subtract off plugging in the bottom bound. So to prove this, let me just start off by defining a function. Big G of x is equal to this integral. That means, G is an antiderivative of f. Okay, so I have that. And I'm saying that f is continuous on the closed interval AB. Now, I'm going to define another function. Big F of x is equal to big G of x plus a constant. Because remember, and big F is an antiderivative also of f, little f. And remember, antiderivatives differ by a constant. So it's fine for me to do this. If I say that g of x is an antiderivative of little f, I can also say big F is an antiderivative also, plus a constant. So there's nothing wrong with me saying this. I just defined it that way. Now let's go back and say, okay, let's find f of a. Well, f of a is equal to g of a plus c. Now, if you look at evaluating, g of a would be just replacing the x with an a. And of course, if I do that, I just get a 0 for the integral. So what happens is I have f of a equals c. Now I have my new function. Instead of f of x equal g of x plus c, I have f of x equals g of x plus f of a. Now let's go the next step and plug in a b for x. Okay, so I plugged in a b into the function, and now I get g of b plus f of a. See, just plugging into the function. That means that f of b is equal to the integral from a to b f of t dt. Just plugging into the original up here, plus f of a. Now if I subtract f of a from both sides, I have the integral is equal to f of b minus f of a. Now that is precisely what I wanted to prove. That's what I was trying to prove up here, and that is the end of the proof.